Welcome to the Energy Transition Technology Chat. I'm joined today by Michael Walsh, the General Manager for Smart Wires here in Europe. Michael, welcome and thanks for taking time to have a chat.
Thanks, Kevin. Looking forward to talking with you.
So, Michael, for people that may not know you, can you do a quick introduction?
Yeah, certainly, Kevin. So I've been in the power industry for about 20 years now. Originally did a PhD in electrical engineering in University College Dublin in Ireland. After that, I moved into the ESB in Ireland, where I worked on a various amount of operations issues, ancillary services, all the technical issues, looking at opening up a new market. Did that for about 10 years, then moved to the Irish Wind Energy Association. I was chief executive there for 4 years. Very exciting time when wind was really going from being the annoying toddler stage of the power industry to being a slightly more troublesome teenager, and really great fun trying to work through that transition. Went from there back into EirGrid, where I was director of Future Grid, looking at essentially the smart grid technology strategy for developing the power grid into the future. And about 3 years ago, I moved from there to Smart Wires to lead the European business, and it's been an amazing ride, and looking at the same problem from so many different perspectives. It's been fascinating.
So, can I ask? Many folks may not be familiar with what Smart Wires do. So what do you guys get up to?
Yeah. We're at that sort of interesting stage where we're getting a little bit more well known, but not quite there yet. So it really is formed on the insight that we're going through this once in a generation transition, or maybe once in an industry era. Like I've heard people say, if people from the early telecoms industry, Graham Bell, etc., came back and looked at an iPhone, they wouldn't recognize it. But if Edison came back and walked into a substation anywhere in the world, he could more or less figure out what was what and how it was working. And largely because the technology is very good and did an amazing job for so long. But we're getting new challenges now as we try and fight climate change and decarbonize. And we're trying to bring in new energy from new natural sources like wind and solar. And that's created a new range of technical challenges about trying to be better at using power when we need it. Also, these sources tend to be in different locations. So very often you have to set up those resources where the generation is available. That can be very different to where the demand is. That can leave you at a bit of an infrastructure gap. And most renewable developers you meet anywhere in the world will complain that, I've got great projects, great resource available, but I don't have a transport. I have no way of getting my power from where I want to generate it to where the consumers are in the big cities. Of course, traditionally, 40, 50 years ago, when you were building new coal, new nuclear, new gas, you could build new transmission, and that was it was a much more I suppose accepted way of doing things at that stage, was to build large new high voltage power lines. In the Western world, that's not really the case, and we're now in a world where in all aspects of our existence we're trying to do more with what we have already, rather than creating new assets that use up resources, have an impact on communities, etc. So the insight behind Smart Wires really was that's going to be one of the big challenges for us in the whole decarbonisation journey. And when you actually crunch the numbers, really surprising insight is how low the utilization is on a lot of these assets. So very often you go to a power system and you find that there's a barrier and they're not able to connect new renewables. But when you look at the numbers, you find there's actually only maybe 20-25% utilization on these network assets. And what Smart Wires does at its core is it puts in new technology that allows you to increase that utilization up from 25% to much higher numbers. And that allows you to connect up new renewables and transport them on the grid that's already there. It means you can get much faster connections of the renewables. It means it's much cheaper because you're not building new infrastructure. And it's also much more sensitive to the environmental and community impact of infrastructure. So at its core, that's what we're trying to achieve.
Now, many folks will be well aware that you have, as you say, traditionally you had the big bulk sources of generating electricity, hydro or power or coal or nuclear, whatever. And as you say, all the wind farms and large solar farms and have come in. And people will be aware that there's the big transmission line taking the power from the power plant to the city. Now, when I started getting involved in the energy industry, I started to understand that, yeah, of course, well, there's a big copper cable or lots of big copper cable. But like a motorway or a road system, there's only so much power. The laws of physics dictate that there's only so much power can flow through. Now, many of the folks listening to us chatting here may not be, or they may be like me. They missed that day in school when we were doing power electronics. Could you give us a kind of a primer on what goes on in a transmission line? You have things like the rated capacity, you have the grid congestion. What for the layman, what is this stuff?
Yeah, well, I love your analogy about the road network because it's a brilliant example. And you know, when we think of road networks, we often think there's a couple of different ways to get from point A to point B. And you know, over time, people get clever and people, you know, that use different routes. And we sort of, as, you know, a very intelligent society, balance ourselves out over those routes. And now with tools like Google Maps and what have you, we're much better at, you know, if there's congestion on one road, we'll sort of be directed, or we'll learn by dint of experience to go a slightly different direction. Yeah. Electricity doesn't work that way at the moment. The electricity, you know, when it's looking for a path from A to B, it looks simply like which one is the shortest path, where is the big motorway available, and everything heads for that route, or it'll head for the shortest line or the line with the lowest impedance. But essentially, it decides which one to go. And once that line gets overloaded, that's it. You can't transfer any more energy from A to B. Even if there's spare capacity available in some of the alternative routes, the electricity just, it follows the laws of physics, so it goes where the laws of physics tell it, that's where it goes. So if that's sort of overloading one path, so be it, I'm finished, I'm blocking up this path. It doesn't have the wherewithal to go on a different path. And that's what our technology essentially does. You put in our hardware on those circuits, and what they can do is they can watch what's going on, or the power system operator, the controller, whatever way you want to set it up. And they can say, okay, this path is now getting overloaded on this one, but I have this alternative path down here where there's spare capacity. And it can actually move the power off the overloaded line onto the ones that have the spare capacity. And in some of the examples we're looking at, you know, you're talking about enough power to, you know, the sort of amount of power to power a full city. You know, that's the sort of increase in transfer capacity that we can put against a very complicated corridor. So it's very substantial when you start getting clever and moving this power between all the different lines to get the maximum amount across what's there at the moment.
You know, I think one of the times when I came across the implications of grid congestion, you know, as you mentioned earlier, way back when things were, let's say, simpler, people would plan out, okay, well, we're building a power plant here, we need a transmission line, we know the rated capacity, we know the amount of it's going to generate, and I wouldn't say it was easy, but there wasn't that many variables. So now suddenly I want to put a wind farm somewhere offshore or whatever. When a couple of years back, when Germany turned off all of the nuclear fleet, the grid congestion changed overnight, because all those nuclear power plants that were generating and pushing stuff onto the established grid suddenly stopped, and then the electrons were coming from somewhere else. And it created all sorts of new bottlenecks and whatever. So when I started seeing that, I was going, wow, I had no idea, to your point, that there was so much planning and stuff goes on behind the scenes. Most people didn't realize that. Now, you also mentioned, and it's been in the news recently, in terms of if a power line reaches a overcapacity because there's too much going through, bad things can happen, right? Either it'll trip or it'll melt or whatever. Is that true with transmission lines?
Yeah, and generally, you know, the operators will control the system so that that's avoided. So they're very good in the operational time frame of figuring out, look, what can go wrong, and I make sure here's all the possible problems I could have, and for any one of those, I set my system up so that nothing too bad happens. And you know, most of the time we have good, reliable power, and that works out. The problem with that is, you know, to actually do that, you sometimes have to spend a lot of money. So it may be that, well, I can do that, but it means I have to turn off all these wind farms over here that are very cheap to actually cost nothing to run in real time. And I have to run a coal plant somewhere else in my grid to make sure I keep it all in balance. So in practice, you know, you're right, the bad things can happen. if you're not very careful how you operate your power system. But the operators, they're good at what they do and they keep the system secure. But very often the costs of that are, they're running less renewables than that are available. They're spending a lot of the consumers' money, maybe using more expensive generation that ultimately comes back to bills. It may be that they're slow in connecting some new renewable source that wants to generate. It might be that they've large new industrial demands that are a bit slower to get a connection. So they have a lot of tools and levers at their disposal to make sure that they prevent from the bad things. But the cost of that and the inflexibility is huge. And I want to just go back to something else, the way you described it, and about the way the planners looked at it. And for, I suppose, generations really, planning a transmission system, it was a hard job, but you were dealing with a lot of known facts and very predictable things. You were dealing with a generator that maybe was going to take 5 or 10 years to build. You were probably centrally planning it. You knew, 10 years out where your next generation was going to connect. And you knew your demand, more or less, it was going to grow 1-2% a year, and it did that for nearly, 50 plus years. We now have the world where, as you describe, you have more renewables. Renewables can build in under a year in a lot of cases, and so the generation pattern can change. You have a world where generation can close down, in the example you gave around the nuclears, and it can be quite unexpected. So you can get very quick changes in generation. Your demand can change. You can get a new data center putting a lot of demand in a location, or you can get a lot of consumers putting solar on their roofs, as you see in Germany, and that changes the pattern of flows around that and the time of day. And you're now doing this in a world where, making the traditional changes to transmission is ever more complicated and takes longer. So it does get to this idea that trying to have this modern, flexible, clean power system, it needs a flexible network in between where, if you had designed it, for example, to take nuclear from A to B, and now you want to move renewables from sort of somewhere a little bit off A to somewhere a little bit off B, you want to be able to actually just move that power onto the corridor. You've spent billions building this corridor. You have it operated, maintained. The communities, have accommodated it. You want to use that rather than going and saying, well, I've got to build a completely new line to do this new need. You want to use technology to use what's there already as efficiently as possible so that you can meet the needs of your consumers without imposing undue costs, and so that you can respond relatively quickly.
Now, you mentioned, we used the motorway analogy, and so I'm trying to get into town and the motorway is full. So I sit at the toll booth and eventually I go around another way. Electrons are very clever, but they're not that clever. So they don't find their own way. They'll all still try and get onto the same motorway. And as you say, somebody will just go, I'm closing the road. So all the electrons coming from that wind farm just can't go anywhere. So I have to turn off the wind farm. Now, with your technology, and you've got a couple of different solutions. You've got the Guardian and smart valves and. How does your technology, what do you guys do on the transmission line that fixes this?
Yeah, so I'll talk about the smart valve. It's probably the easiest to understand. And if you think about, let's say we have two roads and one is 80% full, the other is 60% full, just to give simple numbers. What essentially happens is the power, as it's coming to flow, it looks at what the impedance on these lines is, and it just divides down whatever that ratio is. So if say the impedance of one line is 10 and the impedance of another line is 5, then you'll, in simple terms, get around twice as much power flowing in the line that has the impedance of 5 rather than the one that has the impedance of 10. What our solutions do is it turns those from being fixed numbers. You can control them, and you can turn that 10 and 5 into 7 and 7, 6 and 8. You can turn them up, turn them down. It allows you to tune that in real time, so that if you've got the case where you say 80%, one line 80% full, one line 60% full, you can change that so that they're both 70% full and you have 30% headroom in each case. You can load one up higher so that you leave more spare capacity on the other if you want. And it gives you this ability to actually just change how attractive each line looks for the electrons. And it makes one look like a big, beautiful motorway that they all want to travel on. And it can make that look a little bit less attractive and make the sort of little country road a bit more attractive with the spare capacity on that. And it does that we put our technology on the transmission lines, so they're connected in substations. We can connect them along the line route, wherever, you know, it makes sensible. They're very compact devices. And then the power system operator can just in real time decide. It's almost like just giving a dial to control up and down the power flow on the lines by matching how attractive each of them are to the flow of electricity.
And now when we publish this out, I will put in links to the website, and you've got a whole lot of videos there so people can actually see the devices being mounted onto transmission lines or in a substation. And as you say, it's a valve. So in real time, the network operator can go, as you say, let's balance things out. And make what I found fascinating when I came across you guys last year at the InnoGrid conference in Brussels was that it was all about managing the assets that were there, because, you know, I personally believe there is need for extra transmission lines in certain parts of Europe or certain states or whatever. But yeah, it's challenging to get those built today, right? For all sorts of good reasons. But it's fascinating to see the way your technology works. Now, folks can go to the website, and, you know, I'm reading this here. So you guys use static synchronized series compensators. So the technology underneath this is pretty heavy duty, right? It's not a big wire clamp.
No, it's not. No, it's very clever technology, and, you know, but the core, you know, thinking and knowledge and, you know, the components we use, it's very, very reliable. It's industry standard. We spent an awful lot of time and effort. We've over 1,200 device years now of, you know, out in operation. So it's new and it's clever, but it's also tried and trusted, if you like. We were very conscious of the need to develop technology that's going to work properly on a power system, that's going to be safe, that's going to work with protection systems, that's going to do all these good things. So we've made a huge effort to make sure that it works well and fits within the existing system without causing, you know, any new issues or problems or difficulties. And again, that's something we've been incredibly successful with. And that's probably, I suppose, the secret sauce a little bit. It's taking the clever new technology, but developing it in a way that fits neatly into a power system and works in a way that power engineers can understand, that they can model, that they can figure out, and that they can be, you know, really assured that it's going to operate the way they want it to, and you know, and enhance the security of their system.
Now, on your website and on your social media channels, you guys show a number of case studies and utilities and power companies around the globe using your technology. Could you give us a couple of examples of who's using it and what they're using it for?
Yeah, I'll give you a couple. So I'll start maybe in the UK with UK Power Networks. They're using one example where, very similar to the one we described, where they have 3 lines going from, you know, essentially their substation out to an area where they'd like to connect up more renewable generation. At the moment, you know, one line is a lot shorter than the other 2, and because it's shorter, it looks a lot more, it's like the good road that everyone wants to drive on. And that line was, you know, taking much a higher share of the electricity than the other 2. And essentially that was now, if that was getting fully loaded, that was limiting how much renewable capacity could connect. And what they did with our solution was they put it on the other 2 lines to essentially or on that line and the next line to rebalance, so that all lines looked around the same, so that you could end up bringing through more electricity. And that allowed them to connect an extra 95 megawatts of generation without having to build any new lines. And again, you can find details of that on the UK Power Networks website. I think one interesting one that we're really focused on at the moment is the mobile project. And I'd like to talk a bit more about that in a minute, but we're doing the first project of that in Greece in the next 2 months. And the beauty of that technology is it can be installed in hours. So, you know, we were talking earlier today in Ireland to a renewable developer who sort of had almost become resigned to the fact that it takes 5 years to do anything on a transmission system. And we were sort of saying, well, look, we can't accept that. That just can't be how we think about the world. Our fixed solutions can be, you know, from the time someone wants to move to when they're installed, can be under a year. Our mobile solutions, you know, we're designing these to be fully transportable on roads. They arrive in on wheels. You'll see a video on our website. And these we now have so that they can be installed in under 1 day on a transmission system. So it's just, we need to fundamentally change how we think about the power system. If we're thinking, you know, I have this problem and it's going to take me 5 years so I can do nothing, it's very, it's not a nice world to be in. And part of the challenge for us is to maybe open up people's minds to say, you know, there is this spare capacity available, and I can use it for a temporary problem. I can use it to enable an outage to construct a larger asset. I can use it as an outage to connect up a wind farm, a solar farm. I can use it to solve a congestion problem that's really bothering me. And, you know, I can look at that problem now in March, and I can imagine, you know, by October, I can have this problem solved. And that's not something that, you know, people in the power industry have been used to. And I think that's probably part of the power of the tools we're offering, is that ability to really address something much faster than was ever conceivably possible before.
And in terms of the technology in the mobile solution, is it the same type of technology that you would physically attach in the other products, or is it different? Or
yeah, so the core power flow technology is exactly the same. It's just a way more, I suppose, faster. It's designed for speed of connection. So we optimize it so that it can be transported on the road, so that we can road up to a site for a fast connection that needs minimal outages. So it's taking the exact same technology and just developing it in a way, or deploying it in a way that enables it to get connected incredibly quickly. Like our fixed solutions are fast, but this is, you know, orders of magnitude faster. And it sort of lends itself to some of the most complicated problems where people have been struggling. They want to do a bit of work on a line. They need to take an outage to do it. And the outage is getting that outage to do the work. And it gets into a vicious circle that year by year, the problem gets worse, but so it gets more difficult to get an outage. And, you know, we're trying to break some of those cycles and give people the tools they can use to really address some of the thorniest, long-standing problems they've had.
Now, when I met you guys up in Brussels last year, a lot of the work was around transmission, let's say the traditional transmission system operators, so the guys with the big cables, big pipes. Do you see this technology being used in coming down the grid into whatever, the start of the distribution grid, or where can it play?
Yeah, absolutely. You know, I see in the future it's going to be on every single power line everywhere. I think it's just, you know, the idea in 20 years' time that you used to let power flow wherever it flows. You know, if you think about the internet, and every single junction is a router, and it optimizes where the power flows, power system, or where data flows, it's going to be the same in the power system. We're going to have a completely controllable grid. Now that's you know, we're about 2-3 steps away from that. I think the first step is the problems we're dealing with, where we look at existing congestion, where you have a bottleneck, and we resolve that. I think the next phase then is going to be looking on distribution networks, where very often, you know, the lines are just connected to single wire, so there isn't as much scope for pushing and pulling. But that leaves itself with way more spare capacity, unutilized capacity, than you even have in the transmission system. So when you go down to the distribution system, the utilization factors in many cases are even lower. And it gives you much more opportunity if you can start, you know, looking at clever ways to put your assets on a distribution system and connect them up, where you're getting, you know, more solar connection, where you have EV charging, where you have so much clever stuff happening so close to the consumer. If you can allow that more flexibility to trade over a larger area, then it gives people more opportunity to participate. You can get more solar PV on houses because you can now start sharing it among a wider group of neighbours. You can get more EVs charging. You can use, you know, at the moment, if you want to, you know, use your solar to charge your neighbour's EV, if you're not on the same line, it's going into the bulk system and moving around somewhere. But if you can start connecting up these local wires and controlling the flow of power around, you can then do way more powerful things and make this whole energy transition happen much quicker, because the ability of the distribution networks to, you know, take electricity and transport, to take the, you know, huge amounts of solar coming, that will be a barrier to the energy transition. And it'll also be a barrier to, you know, people want to participate in this. They don't want this to just be a big business event where, you know, it's just big business build large scale facilities and it flows down. You know, there's a huge appetite for people to take part. And our technology, it means you can bring much more flexibility to how you use your distribution network, and use that flexibility to enable people to do those things they want to, help us fight climate change.
Yeah. Where I found it fascinating with your technology was for the past 12 or 18 months, I've done a lot of work with blockchain companies, and a lot of them are looking at, let's say, we'll do peer-to-peer. So I've got solar in my roof here. I'll sell my electrons to Jim or Mary or Bob or whatever down the road. And if you look at the energy union vision, well, theoretically, a consumer could I could sell it back to you guys in Ireland. And then typically the grid folks pop up and say, yeah, but Kev, you don't understand the laws of physics and the way the electrons flow, and you have to map it all together. And it is complex. But this is where your technology comes in, because then you can start, as you say, managing the flow of the electrons on the local grid, which is not something that, typically electrons went off and did whatever they wanted to do themselves, fascinating.
Yeah. No, I think that's good the way you described it. Yeah, so it's an exciting time. I think, look, the blockchain, they give you the business model where you need it, but you also need, you need the two things. You need the business model, but you also need the physical enablers. And, we're at the early stage of looking at how it works, but it's, as you get new technology, it makes things that, even a few years ago, people thought were impossible, they become possible. And then very quickly they become, almost, people wonder, how did we ever do it any other way?
Yeah. Why didn't we think of that before? But yeah, I know, because you see a lot of the new innovative business models around peer-to-peer, transactive energy, microgrids, yada, yada. But yeah, a lot of them look really good on paper and an Excel spreadsheet, because they assume we're all living on a copper plate and electrons can go everywhere. As I say, the laws of physics haven't changed. So this is where you need the combination of the physical and the business models. So it's fascinating. Wow, cool. Michael, if people want to find out more about yourself or about the company, where should we send them?
Smartwires.com, Kevin. You'll find all the information you want about myself and the company there, and you'll have all our contact details, and we'd be delighted to hear from you.
No, we'll add all those into the notes here as we post it out. Michael, thanks very much for taking the time to have a chat.
Thanks, Kevin.
Thank you.
Enjoyed it. Bye now.